Good morning to one and all. Department of Mathematics, KPR Institute of Engineering and Technology, Coimbatore, Tamil Nadu, proudly conducting a 5-day faculty development program on applications of mathematics in engineering. Today is the last day. Highlight of the program is that all the experts are engineering faculties elaborating the importance of mathematics in their disciplines. A commendable knowledge transfer extravaganza even during COVID-19 lockdown period and quarantine. It is indeed a great opportunity bestowed on me to extend a delightful good morning to one and all who have gathered here online through interactive media platform using modern electronic appliances and be enthusiastic participants in the 5-day faculty development program on applications of mathematics in engineering. First of all, on behalf of the KPR IET management, Principal Dr. M. Agila, CE Dr. A. M. Natarajan sir, I feel grateful and fortunate in welcoming the resource person, Dr. V.Manikandan, Professor Electrical Electronics Engineering, Coimbatore Institute of Institute of Technology, Coimbatore, Tamil Nadu. To this August online gathering, I welcome you, Dr. Manikandan sir. I am delighted in welcoming all the participants who have gathered here online from various parts of the globe. I sincerely welcome you all to take part in our seek to disseminate information and empower the academic as well as the student community all across the globe beyond our and any boundaries. Also, I wish to place on record my sincere and genuine thanks to our KPRIET management, beloved Principal Dr. Akila, CE Dr. A.M. Natarajan, for having permitted our mathematics department to proceed with all the essential support to conduct this 5-day faculty development program on applications of mathematics in engineering. For the next 60 minutes, also Dr. V. Manikandan will be elaborating on the topic machine learning models for electrical engineering applications, making an earnest attempt to reach out to satisfy and quench the intellectual needs of the participants. Now I request our HOD, Dr. K.S. Ramasamy sir, to introduce the resource person.
Thank
Sir,
you, Dr.
please.
Karthi. Good morning, everyone who has gathered here online. Dr. V.Manikandan is working as Dean Planning and Professor of Electrical and Electronics Engineering at the Coimbatore Institute of Technology, Coimbatore. He has more than 2.5 decades in this teaching profession. He did his B at Government College of Technology, Coimbatore, and ME at PhD College of Technology, Coimbatore, PhD at Government College of Technology, Coimbatore. And his areas of interest includes fault diagnosis, fault tolerant control of analog and circuit systems, analysis and synthesis of dynamic systems, modeling, analysis of complex systems with neural networks, fuzzy logic based systems, meta heuristic computing system. And he has more than 33 publications to his credit, and also he's doing consultancies in the area energy auditing, design of passive filters, energy auditing, and also he has guided so far 7 PhDs, and he is a recipient of various funded projects from central government and state government for the conduct of teaching learning center and also several other educational type services. One or two to mention, received a sum of 9 lakh under Project Center of AICT New Delhi for the title Center for Advanced Studies in Engineering Technology. Received a sum of 48.82 lakh under E-Learning Center scheme of AICT New Delhi for the title CET Center for E-Learning, and also received a sum of 7.5 crores for the establishing teaching learning center under Pandit Malaviya scheme. So it is our fortunate and privilege to have such an eminent personality with us. Now I hand over the session to Dr. V.Manikandan and request him to start his speech. Dr. Manikandan, please, sir. Dr. Manikandan, you can proceed, sir.
Is it audible, sir?
Yes, sir. Proceed, sir.
Yeah, thank you very much for your nice introduction. Good morning to all of you. And so today, my topic, and it's an application of machine learning in electrical and electronics engineering. how machine learning algorithm could be used to find a solution for engineering and problems. So primarily here, I'm working on analog circuits and systems. Therefore, today I'm going to discuss two things: how the regression and the classification algorithms are useful in finding the faults, that is, remaining useful life of components which is used in an analog circuits. And for this, I'm going to explain with one case study that we already published this paper, this particular work in the Journal of Electronic Testing and Springer. So first we will start with an introduction. So anyway, I will start with very basic. And this is my presentation plan and what is machine learning and what are the types and all about the machine learning. The second, and after that, and we'll move on to the regression and then the classification, and finally, and I'll be discussing a case study with an analog circuits and how the remaining useful life and prediction will be done by using this regression and classification algorithm. It's of course, it's a part of machine learning. And so machine learning, it is way back to 1959, and it is not something new. It is proposed in 1959 itself, where to improve the ability of the computer to learn without being explicitly programmed, and which is proposed by Arthur Samuel in 1959. And basically, if you take machine learning, of course, everybody knows, and many and all and the participants, of course, you might be knowing and the different types of learning algorithms, that is conventional type. There are different state of art and conventional types of learning techniques are available. For example, an SVR and support vector machines and ARIMA and many other LSTM, many other techniques are there. And these are state of art techniques. And well-known topic when it comes to learning, it's neural networks, fuzzy, and many other tools are being used for solving engineering and problems. And machine learning, when it comes to machine learning, there are three types. Of course, it's a supervised and unsupervised and others. And it's called reinforcement learning. Supervised in the sense when we have the target by using an input and output, and with the known output, if you train and you can achieve the result, and it means once you get the convergence, and that is called the unsupervised. And the definition for actual supervised learning is the machine learning task of learning function that maps, of course, the input output. And by knowing the output, and if you train the network towards the output, and it's so called to reach the target, then it's called the supervised learning. And unsupervised in the sense for without knowing the target, if you train the network and reach the solution, and that is called an output, it's called an unsupervised learning. But in real time, most of the problems, and we use an unsupervised learning category because most of the prediction, it's called the forecasting problems. Generally, we use it using machine learning concept, which is highly unpredictable. Therefore, we go for the unsupervised learning category. And supervised, and it's only for simple and solutions, simple problems we take, and we analyze by using supervised learning. For example, in neural networks, there are, again, it's a type of supervised and unsupervised category of networks. And you just take perceptron and ADA-line, MEDA-line, backpropagate network. All these networks that comes under the supervised category. And coherent self-organizing map and all other type of network which comes under an unsupervised where, and we, without knowing the target, we're supposed to train the network. And of course, there is 100% the contrast with respect to unsupervised. And it's called self-learning. It's called self-learning network. And by an intuition, it learns itself and predicts what will be the, and approximate what will be the and future output. So that's called the unsupervised learning. And when it comes to an application, machine learning, it's a talk of the town. Of course, it's it's an upcoming area. And many researchers, of course, nowadays they are applying the machine learning concepts like machine learning, deep learning. It comes under AI, right? Artificial intelligence. Then it comes to machine learning. Then your deep learning, which is the subset of this machine learning concept. So wherever, because machine learning would be very useful where, and we use the bulk amount of data, and especially, for example, we applied this deep learning concept for and analyzing, forecasting, and loads, and which is it's called using and smart meter data. And there are different applications. Wherever you see the machine learning now, it's completely dominates the entire system. And there are a lot of applications. You can, anything you can name where we are applying the machine learning and concepts. For example, and the product recommendations. In product recommendations, in the sense what nowadays, and suppose you go for a search for some kind of products in Amazon. Next time when you and log in and to Amazon, automatically will get the pop-up because the system itself has the intelligence to understand what is the type of requirement that you have. So based on that, it gives the pop-ups. It shows the interest, right? So it understands your brain. It can judge. It can assume that where the system can understand, because the system with now it's an intelligence. It can understand what is the and your like and dislike. Based on that, it provides what it gives the pop-up. So in addition to the product recommendations, now it is where the machine learning concepts are being used in image recognition and, for example, automatic language translation and medical diagnosis and stock market trading, and even online fraud detection can be done. Then virtual and personal assistant nowadays we are using. Then email and spam, and in addition to email spam, we also use to find this machine learning concepts for malware and filtering. Then and traffic also we use, it's called traffic prediction. And finally, of course, it is and speech recognition. So these are the areas and primarily that we are using the machine learning concepts at present. This is what are the areas which I have mentioned here. It is only some of the areas. So there's a big list where there are a lot of scopes for the machine learning algorithms. You can apply those algorithms in order to find the solutions, right? So what is regression? Of course, regression. Of course, it is it's a statistical process for estimating the relationship between the dependent variable and one or more independent variables. And the classification, of course, it's also a type of clustering, and clustering comes under unsupervised, and it's a part of classification only. And the classification, it's a concept which basically categorizes a set of data into classes. There are two examples here, a simple example for understanding purpose, and I gave these two definitions for regression and the classification. Mainly the regression analysis are used for forecasting, and for it comes under a supervised category. And for example, I want to predict what will be the demand of the electricity for the next 7 days. I can use some kind of regression analysis. And the second point, and what's the meaning for classification? For example, I want to assign electricity consumer to different classes, and based on the number of users, because each user has what different applications. For example, users are classified into more than 500 units are classified as high user. Then medium user, it's less than 500 units, and low, it comes under less than 200 units. Okay, so these are the example and the definition, right? You can understand very easily what is meant by a regression and what is the meaning for the classification that we use it. So mainly these two concepts are used here in identifying the remaining useful life. It's called the fault classification of what the analog circuits. Okay, so and here we use linear regression and for electricity demand and prediction, and here. And for example, this is the it's called the flow. How we are training, how we are doing this, we are running this regression and algorithm in order to predict the requirement or predict the electrical demand of an household. Okay, so we take some set of data, then it is processed by learning algorithm. We know, and it is a type of a supervised learning. So definitely we can reach. We have an independent, of course, the dependent variable, output variable. So by using this, we can train, and we can take the output, and also we can predict what is the requirement of electricity for the next 7 days. We can predict up to 7 days or 30 days and so on. And based on the amount of data, based on volume of data, that is what we do. For example, you just take an AccuWeather or a railway reservation, we can understand, we can very well predict. There is an application, mobile application called a TrainMan. So by using TrainMan application, you can understand what is the probability of getting the seats, right? Confirmation. So there are a lot of algorithms, prediction algorithms are available in the literature, And nowadays, everything based on, because now the data, if you have more and more data can be utilized effectively by applying the machine learning concept. Because the state of our techniques, the problem is the state of our techniques and was not capable of handling huge amount of data. And therefore, we are moving on to machine learning or deep learning and the concepts. And this is how we are defining an hypothesis and function. For example, you take a weekday, all 7 days, the unit consumed, then and you can draw, then you will get the and curve, and this is called an hypothesis function. And this is the way about, and we take step by step in order to forecast the household requirement of all the electricity. And that's the definition and for the hypothesis function, and where there are two variables called theta naught and theta 1. Based on these two values only, we will get the curve. So here it is some kind of, and I've taken 3 examples and based on the values of theta and theta naught and theta 1. And the first graph, which indicates when theta naught is equal to 2 and theta 1 equal to 0. And therefore, we'll get flat curve and it's completely horizontal. And second one is the reverse, when theta naught is equal to 0 and theta 1 is equal to 2, then you will get what? And the perfect, it's called a straight line. And both are 1, then accordingly the values, because here, and just I want to tell, and based on the values of theta 1 and theta 1, the functions and varying, and you will get the curve. And then for linear regression, our goal generally is to minimize the cost function, because the generation cost or transmission cost or the distribution cost or whatever it is generally, and the cost function when it comes to an optimization, generally we need to, and most of the cases, and we need to minimize the cost function. For example, and one of the best problem which is used in, which is available in the website for how to design a can, okay, Coke 10. Okay, so with the minimum cost, how we can design the cone, that is very, and this is called how to formulate an optimization problem, that you can very well, you can see. And here, and our goal is to choose a particular value of a theta, and therefore we can minimize the cost function. And cost function, and this is an optimization j theta of not of theta 1, and it's standard and equation which is used to minimize the cost function. And so what is the kind of optimization algorithm that we are using it here? We use gradient, it's called batch descent algorithms. And we change and how the batch descent algorithm, which since here it's a type of convex function. Therefore, here there is a global and local minimum, both are same. Therefore, you just get the convergence. It's called you get minimum by iterating and iteration procedure, and we see to that we get the network is converged. Because in case of when you go for an iterative procedure, we normally fix 2 things. One, we fix the number of iterations, or we fix the target. Okay, for supervised, we can fix target, and otherwise we can fix the number of iterations and see that whether the network is converged or not. So depending on the values, then again we go for the reiterated, or we'll take the output. Okay, so here, and this is the batch gradient descent algorithm. So it is an iterative procedure. I can update by using this updation and equation and see to that, and we're getting the convergence. We can right, there are 2 things I said. Once fix the target, or you can fix the iteration in order to get the convergence. Okay, so learning rate, of course, and to minimize learning rate, it is taken between 0 and 1. When you multiply any product between 0 and 1, and the total and the output, it's called the number of iteration it takes will be. Oh, 1 second. Yes. No. Yes, please. Yes. Please. 1 second. What? Let me know. Yeah, I'm sorry, and okay. Then this is, and of course the derivative, it's called a partial derivative function. So anything if you multiply with 0 and 1 quickly, and in order to, because in neural network itself in back propagation algorithm we use 2 and the factors called the learning rate and the momentum factor. in order to minimize the product value so that we'll get the quick convergence. Okay, so the learning rate is alpha. It is always used in any of the algorithms in order to minimize the product and to get the quick convergence. Okay, so here of course we need to get the minimum and value. It's called global minimum value. Then how to choose the values of what the alpha and dou theta 1 of j of theta 1. When this is when this value is positive, then you will get this is the way where we will reach the output. And when it is, so automatically then the theta 1 decreases. Then when you go for the second one, when the negative slope, when this number is negative, you will get the negative slope. And where theta 1 is increasing. And if you draw, and by taking various values of this theta, and of course based on the functions, and you will get the different values on running multiple iterations of using gradient descent method. Okay, and so here when the alpha, what will happen when alpha is too small, and the gradient descent can be very slow. It takes more time to reach the convergence. Okay, when alpha is too large, also in that case we'll get an overshoot and fail to converge, and because instead of converge, it automatically gets will get a divergent effect. Right? Okay, so you will not get the convergence. So therefore, we need to take an alpha. It's an optimal value of alpha can be chosen to get the convergence at the right time. Okay, then what is the type of classification algorithm? It's called logistic regression, and we use binary classification. And of course, the logistic regression can be used in different types of applications. One, and you can find in classifying an email, and mainly it is used in medical diagnosis for the presence of to understand the presence of the tumor cells. And also, and here in our applications, we use this logistic regression for identifying the faults in electronic circuits, especially the component faults and identification. Okay, so there are, and because we use the concept called healthiness. It's called health and factor. And when based on the output value, when because there are two things, right? When the output is negative, output is 0, or the output is 1. When the output is 0, then it indicates there is no fault in the components. When the output is 1, then we see that the component is fully fault. So in between and 0 and 1, so there where the automatically, for example, when the component is new, definitely the output will be 0 and no fault factors. When the component is okay, for example, beyond certain, and it's called lifetime, and automatically there will be a fault in the particular component. So in between 0 and 1, automatically the component and output, it is naturally day by day because of aging, because of the climate, because of so many other factors. And any product you see and any component you just connect, or any component you can, for example, resistors or capacitor or whatever it is, and each component has its own lifetime. And naturally, and where when the time goes, or when because of the aging effect, the performance started and deteriorating. Okay, so initially the performance will be very high, automatically then the performance starts decreasing, and finally it comes to 0. Okay, so we want to find out and what is the remaining useful life of an component which is attached to a circuit. That is called remaining, it's called an REL. So the meaning for REL in the sense what remaining useful life and prediction of an particular component which is attached to the electronic circuit, right? For each and every component, if you predict how long the component will be present, how long the component will work, and effectively when it is connected to the circuit. Okay, and that is the ultimate aim of this particular and remaining. It's called remaining useful life prediction. By using the machine learning concepts. For example, now recently we have used the KNN for data classification. Right. So now what is, and for that we have to fix the hypothesis function. And what is the output range? And between, because when it is no fault, the output will be at 0. And when it is completely fault, then the output is automatically, it is fault condition. So in between, we have to identify what is the deterioration factor for each and every component. So in order to analyze this and logistic regression, we can use some kind of transfer function. Because it's so-called transfer function in mathematics, we call it as curve fitting. Okay, we can use different types of, it's called a transfer function. In electrical, we say it is called a transfer function. We can use what, and a sigmoid function, binary sigmoid, bipolar sigmoid, and it's called sinusoidal function. So many functions. And then in addition to, in the case of the data is so many very bulk, we can also go for this bell-shaped curve. So there are different types of functions which are standard functions are available in order to make the analysis, in order to understand what is the level of the functionality of a particular component and between 0 and 1. Because some function, because it is, what is the meaning for fault tolerance? Because the component will be present, component is there in the circuit, and with the less fault, the components are functioning with the less efficiency and produces its output. Okay, so this is applicable to anything. Okay, because any product, if you see day by day, because of aging, even you just take a simple tire, and which is, for example, a car tire, and if you see the car tire specification, it is already and it is given like whether the tire is what capable of and where this particular tire is useful up to 25,000 kilometers or 2 years, right? So every product has its own lifetime period and also the usage. Okay, generally, so you have to find what is the remaining, and here an application where here the problem is remaining useful life production. How many years or how many hours the particular component will be present, particular component will work efficiently. That is the ultimate aim. Okay, so, and if the component is completely fault, that's fine. You can remove it, you can replace with a new component. And the component is fully functioning, then there is no issue. But over the years, what is happening? The component starts deteriorating that we didn't know. This is called a soft fault. Okay, so all of them, if the components worn out all of a sudden because of short circuit or because of many other issues, then that is not a problem. Okay, so in between, and we need to identify what is the level of fault that is occurred based on the tolerance, based on some kind of a curve fitting analysis. Here we use sigmoid function. You can use any maybe in electrical we call it as what? It's a transfer function analysis. Okay, so this is g of z is equal to 1 by an e power and minus z. This is by using standard transfer function only we can find is theta of x, and for example, and when is theta of x is point implies what, and 80%, then meaning for and 0.8 implies that an 80% chance of this particular circuit being the faulty. Okay, especially this kind of operations that this kind of testing procedure is used once the product has been fabricated and it is before it is sending to the end market. Okay, before a dispatch, and normally all the products are unchecked. It's called the model-based diagnosis in order to understand whether the particular circuit is functioning or it delivers the proper output or not. Okay, so each and every product that you can see, there is a quality check, right? So if you have the quality check stamp, it means what the function of the circuit or any product, it's working fine. So that is the ultimate, and that is the meaning for what the quality check. Okay, so here we fix the decision boundary, and when we predict y is equal to 1, it means the output is completely fault, and y is equal to 0 means it's functioning. So in between, so what approximately what, when if we have theta of x is greater than or equal to 0.5, then we assume that's 1. It's because we use a binary, and therefore it is 0.5, and greater is we consider so 1, and less than that it is considered to be 0. And the distinct boundary for this is for linear, and we use this particular equation. And for nonlinear circuit, and for linear circuit, then we use this fault, and it's called the decision boundary. And for nonlinear circuit, it's called nonlinear decision boundary. And this is the equation for h theta of the x, and the corresponding graph, and how we are taking the different features, and we are classifying the fault locations, and also the faulty circuit and fault-free circuit, okay, based on the values of what and the h theta of x. So here, now, as I said earlier, we have to minimize the cost function. Therefore, the cost function and the equation is used in order to identify based on the outputs if y is equal to 1 or if y is equal to 0. Okay. So again, and by using some standard procedures where the cost function equation is simplified, and finally, this is the cost function and equation. All right. Then here, And we used an earlier, and we used linear regression and also batch and gradient descent techniques for optimization techniques. So we want to minimize the cost function. It's called J theta. And therefore we go for an iteration, and based on the values of, we can choose proper values of for the alpha and also what the function. It's called learning rate and function. So with this, and we are, and of course, these are the function, and these are the details. And right from the beginning, and what again, I'm just repeating. I hope that time is there. Yeah, still we have time. And okay, so we'll start with machine learning concepts, and there are two algorithms here we primarily concentrating. One is the regression, the second one is classification. Based on that, we use batch descent algorithm, and also we use classification techniques. So here, and finally, and by applying these concepts, and these are the basics and how we have understand. Then what is the background and why we have used this particular algorithm in order to and find the remaining useful prediction for a particular component or a circuit. Okay, now, and once we know all these basics and how to choose the learning rate and how to find the classification, all those things, how to fix the upper value and lower value, it's called upper bound. We call it as what upper bound and lower bound. And in between, how to find the deterioration factor and all those things, how to choose the functions and to fix the upper bound and lower bound. So once you're thorough with respect to all the concepts, then based on that, and we can we can apply these algorithms to a particular and unlock circuits. So now we will move to the case study. And here the prediction, the main and objective, it's the objective of this particular and case study is to find remaining useful performance in analog electronic circuits. Okay, so what we actually did here, and the prediction of remaining useful performance in analog electronic circuits. First we model, so it's pure mathematics. So then we use an health indicator and estimation. Then we find health degradation modeling, and finally we find the fault prognostics. In the sense, what remaining useful prediction, how many hours where the particular component will be alive. Okay, so that we understand after 10 hours, we would like to, because once you know the prediction, then we can, we know that very well. We have to change a particular resistance after 10 hours, after 20 hours, after 50 hours. We know that, and how many hours where the particular component will be alive. So that is a small difference between fault diagnosis and the fault prognostics. In diagnosis, what we do, we classify the fault, whether we understand if we take the particular resistance or capacitors or whatever it is, we understand what is the level of fault at a particular time. Okay, based on that, when the fault is more than 50%, then there is no use of it, I can replace it. So this is all only at the post-production, it's called and generally it is done through an offline, and online is because what we did, it's only an offline procedures. Okay, so the fault prognostics, and the last point is the fault prognostics of Sallen-key bandpass filter. Okay, because in literature, maybe use Sallen-key bandpass filter or low pass and standard, and it's called filter circuits are being used for analyzing for illustration purpose. Okay, so this is second order and the Sallen-key and bandpass and filter. And this particular, and I've taken this and model from the paper that we have published recently, and in JETA, in the Journal of Electronic Testing, and Springer. And this is a standard, it's a second order and Sallen-key bandpass filter. We can apply and Kirchhoff's current law for each node. There are 5 nodes, and from here, node 1 to node 5. Okay, so for each node, we apply the Kirchhoff's current law and form the current equations completely. And so we'll get 5 equations, 1, 2, 3, 4, 5. And for example, if I take node 1, and the node 1 where the first equation would be what, because we take 5 nodes, we can go for the nodal analysis, of course. And there are 2 analyses in circuit theory we use. One is the nodal analysis, the other one is the mesh analysis called the loop current method. So in loop current method, we use when the circuit is closed, then it is appropriate, and it's for open circuit. And when you consider load, it's called node analysis, where we apply the Kirchhoff's current law. And so we take in each node and separately, and we write what equation, it's called balanced equation. And here, and for example, for unit, it's called node 1, and we the input and I input plus V in minus V2 divided by the resistance R1 equal to 0. And when you take node 2, and it is where V2 minus V1 divided by R1, plus in node 2, there are two capacitors are connected. So we'll get SC2, because in S domain, right, we apply this in frequency domain, so it will multiply with the complex, it's called S into C2 into V2. Then, and this capacitor is available between node 2 and node 3, therefore SC1 into V2 minus V3, and plus V2 and V5, right, it's called V0. And this R2 is available in between V2 and V0, therefore it is V2 minus V0 divided by R2. Then it comes to node 3, it is SC and 1 into, and V3 minus. When it comes to node 3, then this is higher in potential compared to node 2, therefore this is taken as SC1 into V3 minus V2 plus V3 divided by R3 equal to 0. Then similarly for fourth node, we can take V4 divided by R5 and V4 minus V0 divided by an R4 equal to 0. Then when it's fifth node, then this is higher in potential compared to node 2. Therefore, it is V0 minus V2 and divided by R2 plus I0. Okay, plus I0, it's output current, plus V0 minus V4 in this area, right? V0, this particular branch, V0 minus V4 divided by R4 equal to 0. Then finally, we can take two things, right? V3 minus and V4, right? It is between, and because we have to take the potential difference between these two, because one is, when it comes to op-amp, there are two inputs called non-inverting input and inverting input. And V3 is the input, it's non-inverting, and V4, because it's basically, it's a difference amplifier, right? So the difference in input is an amplifier. That is the function of basic function of an op-amp, right? Whatever the input and the difference that is here, that the same output, the same, the value will be an amplified, and it is given as what, an output, based on the amplification factor. For example, if the amplification factor is 1, whatever the input, that same output, you will get the same output. That is what the voltage follower is all about. Okay, and based on the gain value only, you will get an output. Okay, therefore, we have to take what is the difference in input voltage between V3 and V4. So these are the first, you have to form this equation and apply KCL, and you can get all the nodal equations called node equations. Once this is formed, then we can convert, because analyzing any circuit through matrix would be very, very easy. Therefore, and we can make a lot of analysis once the values are given, once we form a matrix. So we'll get an 6 by, and it's of course 6 by 7, I think so, right? Yeah, we can form a matrix, and based on these are the unknown values, and there's only one input, because all other inputs are 0 except Vn. Vn is given to In, therefore the particular value we can form, and this is called 1 by G. It's called conductance matrix. G into V is equal to I. Okay, so that matrix they can form, and using this, and you can form a transfer function, right? The transfer function, it is a Sallen-key bandpass filter. It's a second order filter, right? Because the order of the filter is 2. And now we can analyze generally the order of the filter. The order of the filter can be analyzed based on number of storage components. Okay, so here there are two capacitors are present, C1 and C2. Naturally, you will get S squared term will be the highest. Okay, so we'll get second order and S squared term. So if you just see the transfer function, and the transfer function the highest power would be 2, because the denominator, which is, it's only the dynamic equation, of course. Based on this only, we can declare the system and whether it is stable or unstable based on what, and it's called the poles, and the numerator of this transfer function is called zeros, and the denominator is called the poles. Based on the location of poles only, generally we classify, and this is in the form of what, S squared plus omega n into S plus omega n squared into and S squared omega n squared, right? So this is standard, which is available in the standard second order an equation, and S squared plus S into the constant. Okay, and because the equation is right, because it's a standard second order and Sallen-key bandpass filter, therefore the highest power would be 2. And here we have to choose the center frequency, and because from the center frequency only we can identify whether the given, and we can identify whether the particular component is fault or not. Okay. And the frequency, the circuit response, of course, and frequency versus voltage response curve. And here, and we can draw and based on output voltage, and every component is varied, and from 0 to, and for example, if a particular resistor value is 1K, we can vary between and beyond tolerance value. Accordingly, we will get the maximum value. When the particular resistor values and working, for example, if a resistor R1 is 1, then you will get the maximum value output will be 1. Okay, so based on the output value, you will get whether the given circuit, what is the level of fault, and we can understand. So here and here, you can just see the vertical line and where, and it touches 1 and 25, right? So 25 kilohertz is the center frequency here. So this is the maximum value. This is the peak value. Okay, so and based on wherever the component which comes and this particular align to the particular value, then we can say this where the particular and the resistor or the capacitor or the component will be and fine, working fine. When based on the peak value, here you can see the peak value different for different and component. Therefore, depending on the values, whether the component value which goes beyond the tolerance value. For example, normally we use 5% tolerance, plus or minus 5% tolerance for the resistor. We go up to 10% for the capacitance. So here the red line, and of course without fault. This is for when all the circuit components are working perfectly, then this is the curve. Exactly 25 kilohertz, the output will be 1, and you will get the maximum peak value. So where other things, and here the peak value will be different, because sometimes there are two values, because positive tolerance and negative tolerance. And for instance, you just take a resistor value of 1K, we can go up to 1.05 and 0.95. So within when the resistor value varies within the tolerance, of course you can use that particular resistance value, can fix. Therefore, the output will be fine. So when the resistor value goes beyond that particular value, automatically deteriorates, then the output will be low. So we need to identify what is that. So in order to identify those values only, we use this and frequency response plot. So you draw the frequency versus output. Based on that, you can identify. Okay, so now we have to identify the health indicator. How to identify the health indicator? So it's an HI is the component of the estimated based on difference between actual state and present state of the component, and at the end of each sample you calculate the value. Then you find the difference. Based on the difference, you can understand what will be the health condition of each resistor or each component which is used in the a circuit, right? So in order to understand, how to find health degrading modeling, we use this NFK equation. Based on that, and we identify, we analyze, and because a sample and the values are given here, and based on this values are this particular equation, based on the values of our component between two ends, we calculate what is AK, BK, CK, and DK, and the corresponding values are what are tabulated. Based on this value, we can understand how much what is the percentage of what the degradation of a particular component which is used in the end circuit. So this is the health indicator estimation by using the MATLAB simulation. Of course, there are two values. Of course, here you can see one is the true value, which is it is already plotted. Then by using an algorithm, of course, it is almost the predicted value and the true values almost it is aligning. Okay, so here the 0.5 is the benchmark, the 0.5 percentage. Okay, so it's a time, and what is the time? It's called the health indicator. How much where, and based on this capacitor, how many hours where the capacitor can be unavailable, and after this once it is predicted by using the algorithm where the capacitor can be available up to 450 hours. It's called remaining useful prediction. Similarly, for the resistor can be available, resistor is available, and based on the health index, and here initially it is very high, and where the resistor will be available and for service up to 4,750 hours. So this is the indication of what, and health indication of each and every component which is used in the end circuit. Then what is and the fault prognostics, and how we can identify the end prognostic. It's called remaining and useful life prediction. And there are two processes, and here we use by using state transition matrix. It's all simple and this mathematical time domain equation which is used for understanding and also to find the mean variance. It's called covariance value, and we use the distribution function, and then finally we update the function using an x0 based on the x0 value. So the remaining useful life prediction of a capacitor, and this is the area where we use this particular function. We understand that this is the approximate life prediction of a particular capacitance. Okay, normally it works from 175 to 350 hours or 375 hours. Now, when you draw the graph, when you use this algorithm and you draw the graph almost, and here just you can see that here most of the points where we'll get the clusters, where we get most of the points which lies in the particular touches this particular line. Okay, so most of the points which touches the particular line, which is ranging from 252 and 300. Okay, so this is, and beyond that, how many hours where the and capacitors can work. So we can go up to 350, but according to this particular capacitance will be available, and for it's called functioning and available, and where it will be useful to the circuit from 250 hours to and 325 hours. So this is what the remaining lifetime prediction of a particular capacitor. The same thing it goes for the resistance normally, and it works between 3,500 hours to 4,500 hours. And based on this graph, of course, the estimated value and almost it's the same. And here it is the clusters. Of course, most of the points which touches only at 4,000, and it can be where this particular resistance will be available, and for a circuit and up to 4,000 hours and so on. So these are the 2 points where we can predict how many hours where the and particular resistor or capacitor can be and available where it can be used in a particular circuit. So, and these are 2 things. We applied the concepts, and where we applied the regression and the classification and concepts in order to identify, in order to and find and the fault value of a fault it's called components, which is used in circuit, how well the components are connected, whether the components are working fine, or how much, what is the deviation from the tolerance value, and how well the circuit is functioning, what is the output, what is the deterioration factor of a resistor capacitor. Definitely, and due to many other factors, the values of the resistor capacitors are, and it's changed. It's very obvious that, and because of aging, because of temperature, because of so many and environmental conditions, and these resistors or the components are subjected to change. And how well it is changing, whether the capacitors or resistance are within the tolerance limit or it goes beyond the tolerance limit, that can be determined by using this kind of algorithms. Then beyond that, we also found it's what is the lifetime prediction of a resistant capacitor being used in a particular circuit. So thank you, and if you have any questions, and please let me know, and I'm ready to answer. I'm very happy to give clarification.
Thank you, Manikandan sir.
Hi, sir. Hi, sir. Welcome, sir.
Dr. Manikandan, I have queries. Shall I ask?
Yes, sure, sir.
Dr.
Yes.
Manikandan sir. So you have theta 1, theta 2 represent this line of regression, is it not?
Yeah, yes.
Why we need 2 regression lines, sir?
Because when you go for a particular and component value, we need to fix 2 values, because either the output is 0 or 1. Okay, we need to fix 2 boundaries, lower boundary and upper boundary. Okay, so therefore we need theta 1, theta naught, and theta 1. Because when you take a resistor which may falls, because there may be positive and rise or negative fall. When it is negative fall, when it goes less than 5%, it's called negative slope. And for example, 95% and so on, that is also that is also considered to be a fault. When the resistor value goes beyond this 100, that is also considered to be a fault. Therefore, we need 2 ends. It's called 2 boundary values, and higher value and the lower value. That is the point we use 2 theta values.
Is there any level for maximum value for theta 1, theta 2, sir?
Yeah, definitely, because based on the tolerance value, that's why I said, for example, if you take the resistor value, and resistor, we keep 2 things, plus or minus 5%, right? For capacitors, we use plus or minus 10%, that is the tolerance limit. So once the values crosses these 2 boundaries, then we declare it as a fault.
So if you don't mind, could you go to that slide, sir? I want to have some clarification, sir.
Yeah, sure. Which one, sir?
Theta 1 equal to 0, theta 2, you put some. I think first some.
Yes.
Yeah. So here you are fixing h theta of x equal to theta naught plus theta 1x. Is it not, sir?
Yeah, yes, sir. Yes.
Why you are considering only 3 cases, Professor?
No, it is only an example. Here, just I want to give example how the theta, based on theta values only, the component functions where we can identify. Because when you normally, what happens if when you look at the paper, we run up to 50%. Okay.
Yeah.
And it is only an example to show, and based on this theta and theta naught and theta 1 value, only h is going to vary. Okay. So for understanding purpose, I gave two values. One I made, and theta naught is equal to 2 and theta 1 equal to 0. Just show it is an horizontal curve. Then we have a linear curve. Then finally, and after that, we have a theta naught is equal to 1 and theta 1 equal to 1. We'll get the perpendicular rise. Okay. So we need to get, and y value should be very high, because once the component is working fine, then output should be very high. So based on, because we have to, in case of iterations, we vary the component value from 0 to 50%. So this is only an example how the theta and theta 1 and theta values are and subjected are important, where these two only reflects on the output.
Sir,
yeah.
Whether any non-linear behavioral study can be observed in these things, sir?
No, here the circuit itself, it's linear, sir.
Circuit itself, sir. Okay,
yeah.
Sir. But why you use descent algorithm and everything, sir?
No, to find the cost function, to find the minimum, and to find the minimum value, because in the the regression algorithm will be useful in prediction and not in fault diagnosis, where and health indicator estimation, and because we need to find whether the particular component is healthy or not. So when it is minimum based on the convergence rate only, so because once you know and once you have the optimal, and it's called optimization algorithm, then only we can find. So this algorithm will be useful in finding and the remaining useful life of a particular component. That is what we have used it.
Whether convergence is always guaranteed or not, sir?
Yeah, I hope so. Definitely.
For any iterative process or this.
Yeah, and because we use supervised category, definitely, and once the convergence is, once the network is converged, then only we can finalize the our result, whether it is fault or not, because this paper is already published in JETAS.
Yeah. Okay, sir. In slide 41, sir, I have one small doubt, sir. Slide 41, sir. Previous to this, sir.
Yeah.
Here, x0 are random variables or functions of random variables, sir?
Which one, sir?
x0 superfix I equal to f of x0 1 comma u0, and you wrote something, isn't it, sir?
It is not.
Then you are right. x0 I equal to expectation of x of say E is expectation of what is that, sir?
We actually E is, of course, it's an entropy value, sir.
Not expected, but it resembles the definition of covariance, sir.
Yeah. Of course, it is basically an entropy, sir.
Not mathematical expectation. Because there also we have some E of x minus x1 and x minus x2 for covariance between two random variables, sir. Here also write similar. I want to have small doubt. But you have not mentioned anywhere what does E stand for, sir? That's why.
E stands for entropy only.
E stands for only entropy.
Yes, sir.
How these ideas are directly applied in AI, sir?
See, and of course, these algorithms comes under AI. It's a combination. It's a part of AI only. Because
so machine learning also only AI, sir.
Machine learning also actually AI, and this machine learning is a subset of AI, right? And the machine where the deep learning is again a subset of machine learning.
Okay, sir. Thank you, Mr. Manikandan.
Okay, sir.
Raja, please go ahead, sir.
Yes, sir. Professor V. Manikandan, please do accept our sincere congratulations and thank you for your excellent presentation. It was interesting, informative, notable, striking, remarkable, and fabulous. Everyone has observed elegancy in the presentation and clarity in discussion. I am very sure that the participants would have enjoyed and enhanced their knowledge in the domain of machine learning models for electrical engineering applications. I have been seeking commendable and valuable feedback in the YouTube chat box. The feedback with questions raised by the participants will be sent to you immediately. The participants are provided your email ID, so please be kind enough to clarify and enlighten their questions. Once again, on behalf of the KPR Institute of Engineering and Technology, Coimbatore, I thank the resource person, Dr. V. Manikandan, for this nice and wonderful presentation. I also take this moment to heartily thank all the participants for their patient listening. Thank you once more. Thank you, Professor.
Thank you, Professor Manikandan.
Okay, sir. Thank you. Thank you for the opportunity given.